This is a potato. It's 10 years old and it has a GTX 950 and probably no thermal paste left. It's bad. I'm making a game in C++ right now, and this is how it looks without optimizations. But it gets even worse, because my game is inspired by Minecraft, and it is a 15-year-old game. So people will expect to run my game on 10-year-old hardware easily. But I'm not settling for little. I want my game to run with cool shaders as well on older hardware. Luckily, 4 years ago when I started working on this game, I didn't have the beast laptop I have today, but this laptop with a mid GPU. So I started optimizing my game from the very beginning. So now, the game runs at 60 FPS on the potato, while on my PC it runs at almost 200 FPS on 16 render distance, all while looking very nice. So going from barely playable to a good stable FPS, today I'm going to go through all the optimizations that made a difference in my game. Some of them are common, and you might know already, while others are less talked about, with a specific one that basically reinvents the rendering pipeline. Let's go. Let's start with the most basic optimization any Minecraft-like game has, removing non-visible geometry. Without this optimization, the game won't hit 60 FPS even on my new laptop, and while it's kinda easy to implement, I still had some challenges integrating it with the new features that I just added. Tell me if you remember rendering a glowstone in Minecraft to X-rays with the world. Have you ever wondered how this works? Well, imagine you have two blocks that are placed one next to the other. In between them, there will be two faces that are basically invisible to you, so there is no need to render them. The result is that if you enter inside the geometry, instead of it looking like this, it will look like this. So where's the difficulty then? Well, to implement this, for every block, I look at its neighbors, and if there is any block covering a face, I just don't draw it. But I can very easily write this in code because the cube shape is hard-coded. I manually add each face of the cube, so I can easily skip any of them. But what about custom geometry? I want to have cool, decorative and functional blocks like this one that I made here. It's especially important I remove their invisible faces, because they already have significantly more geometry than a normal block. But then I realized something. To import these models, I make them in Blockbench. I export them as 3D geometry and load them in my program. So for each face, I can take a look at the geometry and see if that face is just about touching the bottom plane, like here. If so, I can consider that face as a bottom face and hence remove it if there is a block under me. And then I have to do the same thing for the other faces. I got away this time, but custom blocks pose an even more difficult challenge to implement in the first place, with the inverted rendering pipeline that I have. But more on that later, because now we need to talk about an optimization that few people know about. Everyone talks about frustum culling, but few people know about Z-prepass, and it is extremely easy to implement and can even double your FPS in some cases. Frustum culling means not rendering chunks that are invisible to the camera, and the FPS boost is insane, like maybe even 2x in some cases. But to implement it, you need to be very on point with your mess, and for some reason, it's kind of difficult to intersect the camera frustum with the bounding box of the chunk. And looking at implementations online, I have had but little success. Fortunately, I'm using this project as my dissertation thesis. So I asked my teacher for some help, and he gave me his frustum culling implementation that I could just copy and paste, and now we have frustum culling. Very nice. Weirdly though, while playing this game, things weren't always perfect, and trying to figure out where the FPS drops occurred, I realized what the problem is. Think of this scenario. I'm looking in this direction. Frustum culling will remove all the chunks that I can't see, essentially cutting the total geometry to 4 times less. But what if I'm inside a windowless house? I won't be able to see anything outside it. This is where Z-prepass comes into play. It takes advantage of the fact that coloring in the pixels is the expensive part of the rendering process, and it renders the entire geometry without any color, just to the depth buffer once. And then it renders the entire geometry again, but only colors the pixels that end up in the depth buffer. The GPU has a special optimization where if a fragment doesn't pass the depth test, it won't have to process its fragment shader at all, meaning the fragment shader will only run for the final visible fragments, instead of wasting time rendering things that will later be occluded by geometry. If you want to implement this yourself, I have a tutorial, but it will basically completely remove overdraw, and we can optimize it some more by sorting chunks and drawing them front to back to help the GPU even further. But if this was cool, wait until you hear about how I multithreaded my game, because there is a right and a wrong way of doing multithreading that you are probably doing. But after you hear my advice, you will never be scared of threads again. There is a lot of geometry in the game, a lot of things to be processed, like for example, entity updates, block updates, and loading the chunks themselves. So it's natural to want to process these things on multiple threads. Let's take loading the chunks for example. You might think that I have a main thread of execution, and then several other threads that load the chunks. But this is very hard to implement correctly. The main thread and the worker threads share resources, so you need to somehow put mutexes every time you want to touch a resource. Imagine I want to access a chunk, but a worker thread is currently working at it. I need to wait for the worker thread to finish before I access it, essentially wasting as much time as processing the chunk myself in the first place. Here is a very powerful trick that I do, and it not only removes this performance problem, it also makes it extremely hard to introduce bugs. Essentially, you want to remove all these communication steps. Let's look at a real example. I'm loading chunks, and I would want them to be loaded on multiple threads, but the chunks can be modified by the main thread at any time. And to make matters worse, once I load a chunk, I can only upload them on the GPU from the main thread. There is a lot of communication that we have to remove, but here is how to do it. Starting from the single-threaded version of the program, at some point, we have the chunk loading logic. Instead of moving that into separate threads, we want to keep them enclosed like this. So when the program gets to the point where we want to load chunks, we prepare all the work that needs to happen and we submit it to the worker threads, and then we let them execute. And once all of them finish, we collect the result and continue our execution from there. So I'm basically creating a very hard known starting and ending point to my threads, and also I'm giving them all the data that they need up front. So this means I can know for sure no thread needs to ask from data from another thread, and I'm not touching any thread data from the main thread until I get to the ending point. I can modify the chunks wherever I want, except when I am at this point in the program. Here I have to be careful not to touch any thread data and everything will work correctly. And once all threads are ready, they each write their result in their assigned output buffer, and I then read all the results in the main thread and I upload them on the GPU. This is also how I implemented the server. After I do the basic server logic, I update the world, and this happens with multiple threads, where each thread is an isolated region of the world. So I know threads can possibly interact with one another. Like I first split the world and the tasks into smaller regions, and I send one to each thread. So it's impossible they interfere, because they literally don't have access to the data of another thread. And then I have a step that puts all the data back together, so I can continue running the single-threaded parts of the server. There are some technical details to this approach though, so you don't want to just do nothing on your main thread while you wait for the other threads to finish. You can also run one of the tasks on the main thread, so you don't waste time. Or even better, you can do some other tasks that are completely unrelated to the multi-threaded system, while you wait for the result. And then, at some later point in the program, get the result back. Just make sure you don't modify the thread data from the main thread. And if that isn't an option, you can potentially copy the shared data across all threads, so each thread can read and modify it as needed. Finally, the moment you start and end the worker threads doesn't actually mean starting and stopping a thread. That takes quite a lot of time. Instead, we have to use what is called the thread pool. So basically, the thread will stay open, doing nothing but constantly waiting for a signal to start working again. So in reality, the system actually looks like this, but we have a very clear point where we start working with the threads and a very clear point where we stop, and a hard guarantee that here in between there will be no data communication between threads. And now we get to probably the most important optimization of all, vertex pooling. The game is essentially made out of blocks, so then to render a face, you would usually send the face vertices and render it. But this is kind of wasteful. I mean, all the faces look exactly the same. Why send that many vertices? We want a way to tell the GPU to draw an entire predefined face, starting from a vertex rather than specifying the geometry every time. And we can do this with instance rendering. We define the shape, and then we specify the instances. But then we need to split the geometry into all the possible faces. So vertex pooling takes this a step further, and this is how I do it. I render 4 vertices, instance, but I don't associate them with any geometry yet. For each 4 vertices, I send some instance data that describes the shape, texture and position. Then I construct the shape inside the vertex shader using the vertex index that ranges from 0 to 3 and using the current face index. I'm looking up the result from a predefined buffer that has all the possible shapes that I need to draw. This allowed me to use a single 16-byte vertex to store an entire face, along with flags, materials, light levels, and everything I basically need. This is insane. In 16 bytes, you usually store just the position of a single vertex and nothing else, but with my implementation, with 16 bytes, I store the entire face. There is a problem though. Now I can't simply render triangles from vertices. I can only render predefined faces made of 4 vertices. I can do very simple animations if needed, but everything needs to be predefined and placed in the geometry buffer. So how can I load these custom blocks? Well, fortunately, they are also made out of rectangular faces, so I can take those faces and... yeah, right, the model is exported as a list of triangles. So using some help from ChatGPT, I take all the triangles from the model and try to put them back together to create faces. Then I place those faces in the big geometry buffer making sure to save their index for each block, and they also place their rotated version, and that's about it. Now a chunk will also store the geometry for custom blocks, all inside it, so I can just render everything with one draw coil, at the expense of making it harder to animate things. So for that, I can just use block entities that I just implemented for this training done. But not all optimizations are good. So far, I have only discussed the bright side of optimizations, but in many cases, some optimizations may seem good, but they have many drawbacks, like greedy meshing, or some don't even optimize the game, but make it run slower, and worse, like generating the world on the client instead of generating it on the server. So go watch this video if you want to see what optimizations I kept away from my game. See you there.